In this episode, we are taking on a vulnerability that can sound a little abstract at first because the attacker is not always attacking the user directly and is not always targeting the most visible part of the application. Server-side request forgery, SSRF, happens when an application can be tricked into making a request from the server to a destination the attacker chooses or influences. That matters because servers often sit in places users cannot reach, can access resources users should never see, and may be trusted by internal systems in ways that make their requests unusually powerful. For a beginner, the easiest way to think about this is to imagine convincing a trusted employee to walk into a restricted room and bring back information, not because that employee wanted to help the attacker, but because the process they followed was too trusting. This topic matters deeply in CySA+ because many organizations build applications that fetch web content, import files, connect to outside services, or validate remote resources, and every one of those features can become risky if the server is allowed to fetch whatever it is told without strong boundaries. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A normal web request usually begins with a user interacting with an application, and then the application decides how to respond based on its own logic. Sometimes that response involves the server reaching out to another location, such as loading a remote image, checking a feed, pulling a document, validating a callback, or contacting another service to complete the requested task. None of that is inherently unsafe. In fact, modern applications depend heavily on these kinds of server-to-server actions because they support integrations, automation, content handling, and convenience features that users now expect. The danger appears when the application lets outside input decide where that server request goes without properly limiting the destination, the path, or the type of resource the server is allowed to contact. Once that happens, the attacker is no longer just interacting with the application. The attacker is trying to steer the application into acting like a proxy, scout, or messenger that can reach into places the attacker could not directly access alone. That distinction is what makes SSRF so important. The attacker is not merely sending a bad request to the application and hoping it breaks in an obvious way. Instead, the attacker is persuading the server to send a request from its own trusted position. This means the target of the request may see it as coming from a legitimate internal system or from a network location that normally has more privileges than an outside visitor. In many environments, internal services trust other internal services more than they trust internet users, and some resources are designed to answer only when the request comes from inside the environment. If the vulnerable application can be used to send those requests, then the attacker may gain access to internal information, hidden systems, metadata services, or management interfaces without ever having direct network access to them. For a beginner, the simplest lesson is that SSRF turns the server's reach and trust into the attacker's opportunity, and that is often far more dangerous than a flaw that only affects the user-facing surface of the application itself. It helps to compare this to the everyday role of a receptionist or assistant in an office. Imagine an outsider who cannot enter certain rooms, cannot call certain internal extensions, and cannot request certain files directly. If that outsider can persuade a trusted staff member to make calls, retrieve documents, or walk into back office areas on their behalf, the outsider has effectively borrowed the staff member's access without actually becoming staff. That is the basic idea behind SSRF. The application server is the trusted staff member, and the attacker is trying to influence what the server does next. The application may believe it is simply fetching a resource, testing a connection, previewing a link, or processing a legitimate workflow. The real problem is that it has not restricted where that request can go, what protocols or destinations are acceptable, or what internal trust boundaries should never be crossed, even when the request technically came from its own backend logic. Many real-world application features can create the conditions for SSRF, which is why this topic is broader than one specific coding mistake. A platform may let users submit a web address so the server can generate a preview, download a file, scan a remote resource, import data, process a webhook, or verify a callback endpoint. A messaging tool may fetch content from a link to build a richer display. A cloud management portal may test whether another resource is reachable before saving a configuration. A help desk platform might pull an external image or attachment to support a workflow. All of those features sound useful because they are useful, but they also create a moment where user-controlled input can influence a request the server makes behind the scenes. Once you see that pattern, the vulnerability becomes easier to recognize. The question is not whether the feature feels modern or convenient. The question is whether the server is being given freedom to contact destinations it should never trust user input to define. One reason SSRF can confuse beginners is that it sounds somewhat similar to other web vulnerabilities involving requests, yet the trust model is different. In cross-site request forgery, CSRF, the attacker abuses the victim's browser and existing session to send a request to a target site. In SSRF, the attacker abuses the application server itself and its network position to send a request somewhere else. There may be no human victim clicking a button in the key moment, and there may be no stolen password involved. The vulnerable application becomes the intermediary, and the most important question is not whether the user intended the action, but whether the server should have been allowed to make that outbound request in the first place. This matters because the resulting damage can extend far beyond the original application. A flaw in one web feature can become a path into internal services, cloud resources, hidden endpoints, or sensitive information sources that the outside attacker could never have reached directly from the internet. The impact of SSRF depends heavily on what the server can reach once it starts making attacker-influenced requests. In some cases, the attacker may only be able to make the server request public internet locations, which is still not ideal, but may have limited security value. In more serious cases, the server may be able to contact internal application programming interfaces, development systems, storage services, monitoring dashboards, metadata endpoints, or administrative interfaces that were never meant to be exposed externally. The attacker may also use the server to learn about the internal environment by observing which requests succeed, fail, time out, or return useful details. That information can act as reconnaissance, helping the attacker map internal systems and identify higher-value targets. In cloud environments, SSRF has earned particular attention because application servers sometimes have access to instance metadata and service credentials that can reveal powerful information about the workload, its identity, and the resources it is allowed to use. Even when the first result seems minor, the information gathered can quickly support broader compromise. This is why SSRF is often described as a pivoting or reachability problem rather than just a simple input validation issue. The attacker cares about what the server can see and how that view differs from the attacker's own. If the application sits deep inside the environment, has broad network permissions, or runs with strong cloud identity privileges, the possible impact rises sharply. A lightly exposed public web application with narrow backend access presents one kind of risk. An internet-facing application that can talk freely to internal tools, deployment services, secret stores, and cloud control planes presents a much more serious one. Analysts should therefore think beyond the vulnerable feature itself and ask about the server's placement, permissions, and relationships. The flaw may exist in a link preview or import field, but the meaningful risk comes from the trusted position behind that feature. That is what turns a modest-looking web issue into a potential gateway to internal discovery, credential exposure, or administrative misuse. A common misconception is that simple filtering of bad-looking addresses is enough to solve this problem. In practice, SSRF can be tricky because servers, libraries, and network layers may interpret destinations in multiple ways, follow redirects, support different protocols, or resolve names differently than developers expect. A team might believe it blocked obviously dangerous internal addresses while still leaving alternate paths that reach the same resources indirectly. Another team might validate the original destination, but forget that the server later follows a redirect somewhere unsafe. The deeper lesson for a beginner is not about memorizing every technical bypass. The deeper lesson is that weak filtering often fails when the overall design still gives too much freedom to user-controlled outbound requests. Safer design comes from limiting what the server is allowed to contact. mapping user choices to approved destinations, and treating outbound fetch behavior as a privileged action that needs boundaries, not as a harmless convenience step that can follow any path the user supplies. The server's own privileges and network location are central to how severe the problem becomes. If the application server runs with minimal permissions, sits in a tightly segmented zone, and can only contact a short list of approved backend services, the blast radius of SSRF may be limited. If it runs in a broad trust environment with access to many internal systems or strong workload credentials, the consequences can become much more serious. This is one of the most important habits for a security analyst to develop. A vulnerability is not just about whether a flaw exists in the application code. It is also about what the flawed component can touch, what identities it holds, and how much the surrounding architecture amplifies the damage. The same SSRF weakness in two different applications may deserve very different urgency, depending on one server's reach, identity, segmentation, and connectivity. Good analysis, therefore, connects the software issue to the infrastructure reality around it instead of treating all SSRF findings as equally dangerous by default. Detection is often difficult because a successful SSRF attack may look like ordinary outbound traffic from the application server unless the organization is paying attention to where that server usually communicates. Security teams may notice unusual outbound requests, repeated calls to destinations the application rarely or never contacts, unexpected internal connection attempts, odd timeouts, or access to metadata services that do not fit the normal workflow. Application logs may show suspicious user-supplied destinations, and network telemetry may reveal the server scanning or probing locations that are unrelated to its documented function. In some cases, the first sign comes later, when credentials are abused or internal systems are accessed in ways that suggest the attacker learned something through a hidden path. This is why monitoring outbound behavior matters so much. Many teams focus heavily on inbound requests from the internet, but SSRF reminds us that what the server sends outward can be just as important, especially when the server occupies a trusted position inside a broader environment. Mitigation starts with the idea that servers should not be allowed to fetch arbitrary destinations simply because a user provided them. Stronger designs often rely on allow lists, meaning the application is permitted to contact only a known set of approved hosts or services relevant to the business function. Network segmentation can reinforce that choice by ensuring the application cannot reach sensitive internal resources even if the application logic is tricked. Cloud environments may add further protections by hardening or restricting access to metadata services and limiting the privileges associated with workload identities. Teams can also reduce risk by removing unnecessary fetch features, isolating content retrieval services, and keeping administrative or management interfaces off pathways reachable by general application servers. The important beginner lesson is that prevention works best when the environment assumes abuse is possible and limits the consequences in advance. If the application has too much freedom, then one input handling flaw can become a route into many unrelated parts of the organization. Risk prioritization for SSRF should always be grounded in business context rather than the vulnerability name alone. A small public content tool that can only fetch from a narrow external source is not the same as an internet-facing application that sits inside a cloud environment with broad access to internal platforms and powerful service identities. Analysts should ask what secrets, internal systems, or administrative paths the server might reach, whether the feature is exposed to unauthenticated users or only to trusted roles, and whether existing segmentation and outbound controls limit the damage. They should also consider whether the application handles sensitive business processes, because even partial internal visibility can become a serious concern when it touches financial systems, customer records, deployment pipelines, or identity services. This is where vulnerability management becomes meaningful rather than mechanical. A true assessment of SSRF is about reach, privilege, exposure, and consequence, not just about whether a scanner or tester assigned the label to a particular endpoint. There are also broader lessons here about how modern applications are designed. Organizations increasingly want systems that integrate with other services, fetch remote resources automatically, enrich content, validate callbacks, and behave dynamically. Those features are useful, but each one creates a trust decision about what the server will contact and why. When that decision is left too open, the application may quietly become a bridge between untrusted user input and trusted internal access. That is why SSRF is not just a bug to patch and forget. It is a reminder that outbound network behavior deserves the same careful design thinking as inbound access control, authentication, and input handling. Developers, architects, and analysts all need to think about whether the server's ability to make requests has been treated as a controlled privilege or as an invisible background convenience. The answer to that question often determines whether a feature remains useful or becomes a pathway for serious abuse. By the end of this discussion, server-side request forgery should feel less mysterious and much more practical. The attacker is not simply attacking a server in the ordinary sense. The attacker is trying to make the server attack, fetch, or reveal something on the attacker's behalf by abusing the server's trust, location, and reach. That is what makes SSRF such an important topic for new cybersecurity learners, because it shows how a small-looking feature can expose much deeper layers of an environment when backend permissions and outbound requests are not controlled carefully enough. Once you understand that the real issue is not just bad input, but misplaced trust in what the server is allowed to contact, the whole vulnerability becomes easier to recognize and easier to analyze. For a CySA Plus student, that perspective is valuable because it turns SSRF from a technical phrase into a broader lesson about architecture, trust boundaries, and why the safest systems are the ones that assume even their own servers need strict limits on what they can do.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.